Welcome to this episode of Numbers in Medicine. This is part 2 of anion gap metabolic acidosis. In our previous lectures, we discussed the Henderson-Hasselbalch equation and the 4 major kinds of acid-base disturbances. Again, we're going to focus on metabolic acidosis when there's a decreased bicarb and a lower pH. There are 4 major steps to determining compensation and any additional disturbances that may be present. If you follow these 4 steps, you will get every single metabolic acidosis question correct. The first is calculate the anion gap. The second is use Winter's formula to evaluate for respiratory compensation. Third is calculate the delta anion gap. Fourth and final step is calculate the bicarbonate gap and compare that to the delta anion gap. I'll explain each of these steps in detail and we'll do some examples as well. Step 1. Calculate the anion gap. We've already reviewed this equation. The anion gap is the concentration of sodium minus the quantity chloride plus bicarb concentrations, and the normal anion gap is less than 12. Again, differs by institution, but let's go ahead and continue with this value. The second step is to use Winter's formula to evaluate for respiratory compensation. Winter's formula is the predicted PaCO2 is equal to 1.5 times the concentration of bicarb plus 8 plus or minus 2. In the 1960s, Winter was curious if there was a linear relationship between bicarb concentration and the predicted PaCO2. So he had 60 patients with various metabolic acidosis problems and measured their PaCO2 and found this linear trend. If the measured PaCO2 does not equal the predicted PaCO2, then there's another respiratory disturbance present. And we can easily figure out if there's an additional respiratory acidosis or alkalosis by comparing the two. If the measured PaCO2 is greater than the predicted one, then there's an additional respiratory acidosis. That's because if the measured value is higher, we're retaining CO2. And when we're retaining CO2, that's a respiratory acidosis. Conversely, if the measured PaCO2 is less than the predicted one, then there's an additional respiratory alkalosis. That's because we're blowing off CO2, hence alkalosis. The third step is calculating the delta anion gap. Delta anion gap equals anion gap minus 10. We talked about how anion gap should be less than 12, but the typical value for it is 10. Hence, the delta anion gap just shows how much greater than 10 the anion gap actually is. Step 4 is to calculate the bicarbonate gap and compare that to the delta anion gap. The bicarbonate gap is simply 24 minus the bicarb, 24 being a normal value for bicarb. Essentially, the bicarbonate gap shows how far away the bicarb is from the normal value of 24. If all of the delta anion gap is from the drop in bicarb, then we expect the delta anion gap to equal the bicarb gap. If they're not equal, then we know that there's an additional metabolic process going on. If the bicarb has dropped more than what we expected from the delta anion gap, then we're losing more bicarb than we thought, so there's an additional acidosis occurring, and it's a non-anion gap metabolic acidosis. Conversely, if the bicarb has dropped less than what we expected from the delta anion gap, we're holding on to bicarb, hence there's an additional metabolic alkalosis process occurring. This might be a little bit clearer when we do a couple of examples, but it's an important concept to understand. So let's do some examples. A patient with diabetes off of his insulin comes in, and these are the values we see. His ABG shows a pH of 7.2, partial pressure of CO2 is 23, the BMP shows a sodium of 140, chloride of 106, bicarb of 10, and glucose of 400. So we ask ourselves 2 questions. First, what is the primary acid-base disturbance that is present? And are there any additional acid-base disturbances present? So we go to our flow sheet that shows when you have a lower pH, which in this case we do, we have an acidotic process. and then the bicarb is low, so we have a metabolic acidosis. So step 1 is check. We have a metabolic acidosis occurring. Now we need to determine, is it anion gap or not? So let's calculate the anion gap. In this example, it's 140 minus 116, or 24. Remember, a normal anion gap should be less than 12. This is elevated, so this is an anion gap metabolic acidosis. Step 1 complete. Now we need to use Winter's formula to evaluate for respiratory compensation. The predicted partial pressure of CO2 is linearly proportional to that of bicarb. When we substitute our values, 1.5 times 10 is 15, plus 8, 23, plus or minus 2. The measured PaCO2 we had was 23. It exactly matches up with our predicted PaCO2. That means there's no additional respiratory disturbance occurring, and respiratory compensation here is appropriate. Step 3. Calculate the delta anion gap. Here the delta anion gap is equal to 24, our anion gap, minus 10, 14. Now let's calculate the bicarbonate gap. The bicarbonate gap is 24 minus 10, which equals 14. So here the bicarbonate gap equals that of the delta anion gap, meaning the entire change in your anion gap was due to the drop in bicarb. That means there's no additional metabolic disturbance present. And in this example, this patient likely has DKA with anion gap metabolic acidosis. All right, a tougher example. A young man has ingested many of some unknown substance, and he seems to be breathing a little bit fast when you see him. So here are our values. And the ABG, his pH is 7.25, acidemic. His PaCO2 is 10. His B-Mary-P shows a sodium of 140, chloride of 106, and bicarb of 10. What primary acid-base disturbance is present? And of course, are there any additional acid-base disturbances present? So in our ABG, the pH is less than 7.4, so again, acidemic, and our bicarb is less than 24. So this appears to be a metabolic acidosis. Next, we calculate the anion gap. Here our anion gap is 140 minus 116, which equals 24. Notice very similar to our first problem. Again, anion gap greater than 12, so this is anion gap metabolic acidosis. Next, we use Winter's formula. Here, the predicted PaCO2 should be 1.5 times that of bicarb, 10, so a total of 15, plus 8, 23, plus or minus 2. But our measured PaCO2 was only 10, much less than that of our predicted. That means we are blowing off CO2 because our measured value is less than our predicted PaCO2, right? Our measured one is less than predicted, which means that we are blowing off CO2, so it's an additional respiratory alkalosis. Next, we calculate the anion gap. And here, just like last time, 24 minus 10 is 14. And then we calculate the bicarbonate gap, which is also 14. And since they are the same, there is no additional metabolic disturbance. Therefore, this patient likely is presenting with aspirin or acetylsalicylic overdose with an anion gap metabolic acidosis with an additional respiratory alkalosis. Our final example is a patient with no known history, presents with an ABG showing a pH of 7.25, PaCO2 of 30, and his BMP shows a sodium of 140, chloride of 100, and bicarb of 10. So as we always do, we'll determine what primary acid-base disturbance is present, and if there are any additional acid-base disturbances present. We go back to our flow sheet. pH is less than 7.4, bicarb is less than 24, looks like a metabolic acidosis. We calculate the anion gap. Here it's 140 minus 110 is 30. Again, it's greater than 12, so this is an anion gap metabolic acidosis. The second step is to use Winter's formula to evaluate for respiratory compensation. Our predicted PaCO2 will equal 1.5 times 10, the concentration of bicarb, plus 8, plus or minus 2. So our predicted value is 23 plus or minus 2. However, our measured value was 30, greater than that of our predicted PaCO2. Because our measured PaCO2 is greater than our predicted one, that means we're holding on to CO2, so there's an additional respiratory acidosis. Step 3, calculate the delta anion gap. The delta anion gap here is 30 minus 10, which is 20. The final step is to calculate the bicarbonate gap and compare it to the delta anion gap. Here, the bicarbonate gap is 24 minus 10, which is 14. And for the first time, our bicarb gap and delta anion gap don't match. When the bicarb gap is less than the delta anion gap, our bicarb number is higher than what we expected, meaning we're holding on to bicarb. Therefore, we have an additional metabolic alkalosis. So this patient has an anion gap metabolic acidosis, a respiratory acidosis, and a metabolic alkalosis. They have 3 different acid-base disturbances. This was anion gap metabolic acidosis part 2.